Alright, so let's go through the first Cfat here. This one stumped a lot of you guys, and actually, funny enough, I asked some of the other teachers about this question as well, and there were some divided opinions about this question because it is a bit tricky. And I'll show you guys what I mean as we go. So here is a graph that shows the connections between 5 towns. So U, V, W, X, Y. And obviously we all understand what this is saying, okay? So I don't need to explain the connections there. The number of vertices in the graph. So remember, vertices is your dots. So you've got 5 there. Okay, so 1, 2, 3, 4, 5. The degree of vertex U. So degree refers to how many edges connect to that vertex. So for vertex U, you've got 1, 2, 3, 4, 5 as well. Okay, so 5 for U. And then the degree of vertex V. So V will be this one. Okay, you've got 1, 2, 3, 4, 5. And then this should be 6. So let's say it's 7 there. Did I miscount one? I don't think I did. Oh no, sorry. I'm being silly. It's the number of connections. So the loop counts for 2. That's the one. 1, 2, 3, 4, 5, 6, 7. Okay, that makes sense. I'm looking at the edges only. But remember, the degree is the number of lines that connect to that dot. Now, remember, the loop will always count for 2. Okay, keep that in mind. All right, next one is the number of edges in this graph. So just count the number of lines here. Yeah, so you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The reason why I do these little lines is to help me keep count of what I've done so far. Okay, so there's 12 in there. And how many odd vertices are in this graph? All right, so odd vertices, meaning you look at the vertices, okay, and how many lines connect to them. So Y's got 2, U has 1, 2, 3, 4, 5. That's 5. V has 1, 2, 3, 4, 5, 6, 7. So that's 7. W has 1, 2, 3, 4. So that's 4. And then X has 1, 2, 3, 4, 5, 6. 6. So you've only got 2 odd vertices. Okay, easy. Question 6. Now this is where everybody got stumped, and this is also, again, like I said before, I asked some teachers about this. This was very confusing. Now, granted that this question was only 1 mark, you wouldn't have lost too many, but some of you guys might have labored over it for a good few minutes. So just looking at the graph, understand some of the connections and how they work, and also looking at this part of the map, there's some interesting parts here that we need to make note of. Okay, what do these intersections mean? Well, technically what they mean is as is what you think they would mean. You can basically go through them as an actual intersection. Okay, so for example, if you were to go from U to V, okay, you actually have 2 options. Yeah, you can either go this way, or you can also go this way. So that means from U to V, and you can see here, U to V, there should be 2 connections, or 2 edges. And that's sort of how you can understand how these work. Or another example could be like if I was going from W to X, okay? I have two ways to get there. So W to X, I can go this way, but then the intersection here allows me, and here as well, to go another way. And you can see from W to X, you've got two paths. Now, the weird thing is, I have a feeling there's something wrong with this question because there's actually information missing in here as opposed to information missing in here. But the question does say what info is missing in here and add it. Now, you'll obviously notice the first thing I added there was that loop in V. However, the annoying thing is, if you understand how the intersections work, there actually already is a loop in V. You can see here. Okay, but I did ask another teacher about it, and they've said technically a loop should only be to itself and explicitly to itself, which means that there shouldn't be any intersections in that loop. So, but I was like, yeah, but like, I don't know, it's a bit confusing. So I just added the loop so it's explicitly to V to itself. But then another thing that's missing is in this graph, okay, V to W, okay, it says there's only one connection, okay, but technically V to W has two connections in this graph. So you can see V to W can go here, but V to W can also go this way. All right, but it's missing in this graph. Okay, so it's really interesting in the way that this question is framed. I've decided that if you've at least included the loop in this question, then I'll give you the answer for it. The teachers were a little bit unclear, in my opinion, about how we can go about answering this, but I might bring it back to them and ask, like, what's the definitive way of looking at this picture? Again, because of these crazy intersections. All right, but I don't think you'll get a question like this in the SAC, so don't get too scared of it. Let's keep going. All right, this one here, the map of the following 6 states is shown here, and then there's a network for it right here. And what this is saying is the connections between each, basically each state, okay, and how they're all connected. So that means WA can go directly to NT and to South Australia, and then Northern Territory can go to South Australia directly. I'm basically reading the borders, yeah? So Northern Territory can also go to Queensland. South Australia can also go to Queensland. Queensland can go to New South Wales. South Australia can go to New South Wales and also to Victoria. There's a border here between Victoria and New South Wales, and then there's a connection there as well between ACT and New South Wales, and then lonely little Tasmanians by themselves. Now, what I've done here is what you should do actually for this question is I would actually label the vertices properly so you know what's what. Yeah. So this is what I've done here is I've just made it a bit bigger, and I'm going to label the vertices first so I know what's what. I know G is going to be Tassie, okay, because it's by itself. There's no direct connections to it, so it's not connected. Now, what else can we see here? Well, I can see that F only has 2 connections going to it, yeah? What other vertices here have 2 connections? It's WA, okay? You can only have 2 connections to WA, so F is WA, okay? Now, what else do we have? I can see ACT here. You can only get through ACT if you go to New South Wales, meaning there's only one vertex, one edge connecting to ACT, so that means D should be ACT. And if that's the case, the only one connected to ACT is New South Wales, so B is New South Wales. Okay, and so what else do we have in terms of connections? Well, I can see that from WA, okay, there's a vertex here that's got 3 connections. So if I look at Northern Territory has 1, 2, 3 connections going to it. Cool. And then if you look at this vertex here for South Australia has a lot more going to it, yeah? So I would say that E in this case is Northern Territory, and H in this case is South Australia. Okay, and we've only really got 2 more. Let me just move this here, sorry. So you've got Victoria left, and what else did I haven't put down? Victoria and Queensland, okay? So the only other ones I can see here are Vic and Queensland. Queensland, you can go to Queensland from NT, South Australia, New South Wales. So there's only about 2 connections there, 3. So in this case, this vertex here has 3, so this should technically be Queensland. And then this one, C, will be Victoria, because if you look at Victoria, there's only 2 connections that go to Victoria, so C is Victoria. Okay, and that sort of will help you understand how to do the next few questions. So which vertex represents Tassie? Well, Tassie was G. All right, so that's pretty easy. Okay. Which vertex represents ACT? All right, so if you look at ACT, it would be D, not there. All right. And which vertex will represent Queensland? So Queensland would be A, right there. All right, easy. Next one. Okay, so are the graphs in this question isomorphic? Okay, so with this question, understand what isomorphic means. Remember, that means they're exactly the same. Even though they're drawn differently, they have to have the same everything, the same vertices and edges. All right, same number of vertices and edges and same connections. Okay, so you got to have the same vertices and the same edges, or same number of those, and the same connections. Now, given that that's the case as well, even though they're labeled differently, they can still be isomorphic. Okay, so let's see, are these isomorphic? Well, if you look at V1, V1 should be directly connected to V4 and V2. So you can see V1 is only connected to V5, V3, and V2, but not V4. Okay, that means this is already not isomorphic. Okay, I would write not isomorphic. And in terms of writing evidence, I would state specific things about the graph. Okay, so I would say V1 in graph 1 so I've called this is graph 1 here. Actually, let me write my answers here. Oops. I'll write my answers here. Oh, sorry guys. I can't move it. It's alright. Basically, V1 in graph 1, okay, it doesn't have the same connections as V1 in graph 2. So I would say V1 in graph 1 is connected to V2, V4. Sorry, V1, V2 and V4, yep. V4. And then that in a V1 in graph 2 is connected to, hopefully this doesn't get confusing because it's in here, I'm so sorry, V5, V3 and V2. Okay, so they have to have the same connections, and because it's not connected to the same vertices, it's not isomorphic. Okay, hope that's made sense to you guys. It can get a bit tricky trying to prove them, but the only thing I will say is just use what's in there to make sense of what's connected and what's not connected. Okay, that's the main thing I will say to you guys. Let's see if I can move this. Okay, can't. That's annoying. Okay. Alright, so here the following graph shows the links between A, B, C, D, E. And then here the question is make a adjacency matrix. I've made it here. I think I don't need to go through this question because most of you guys know how to do that one already. Okay, so I'll leave that be. Let's go to the next one. Convert the graph to planar. That's the second thing to look into. So we're going to make this graph planar. Remember, planar just means that none of the lines intersect with one another. So if I was to redraw this as a planar graph, remember, start off by drawing the vertices. And make sure that you do your best to keep them in the exact positions. E, D, C, B, A. Now, technically, you don't have to make it exactly the same, but I would suggest, again, keep it in the same exact positions. Just so it's easier to draw your lines. So you know that there's a connection from A to B. You know that there's one from D to C. And then, so E to D, D to C. and there's also one from, let's go A to C. The only other connection is, remember, to make it planar, you can't do this. Okay, the lines cannot intersect. So I can choose to move either B this way, get it connected with E, or I can choose to also do this way to make it planar. Okay, either one is correct. Just pick one or the other. I'll go with this one. What was I doing? Yeah. Okay, this is what I'll go with. The idea is just make sure the lines do not intersect for it to be planar. Alright, given the following connected planar graph, write down the number of faces, edges, and vertices, clearly labeling your answers. Alright, so you're looking at how many faces, how many edges, and how many vertices. Okay, so faces, let's count. You've got 1, 2, 3, 4, and you've also got 5 on the outside. Remember, the outside counts as a face. How many edges? 1, 2, 3, 4, 5, 6, 7, 8, 9. There should be 9 edges. And then how many vertices? I'll just leave that. Would be 1, 2, 3, 4, 5, 6. Okay, 6 vertices. Easy. Last question for this Cfat. Show that Euler's formula works in the connected planar above. Now, if you forgot what Euler's formula is, I think in the notes it's this. V plus F equals E plus 2. That's in the notes that we've given you. In the textbook, it could be V plus F minus E equals 2. They're exactly the same thing, yeah? The idea is making sure that the formula just works, or this equation actually works. That's what we're looking for. You might even see it as a variation of V minus F plus E equals 2. That's also the same thing. The main thing is that there's at least one minus in there somewhere, okay? But in any case, we'll just stick to these. So just make sure you substitute the values that you have here into the formula. So V is going to be 6. I'm going to use this one. So V is 6 plus F, which is 5, equals E, which is 9, minus 2. Oh, sorry, plus 2. Wrong one. Okay. So in this case, looking at the formula, 6 plus 5 is 11. And then 9 plus 2 is 11. So that makes sense. So that means that that formula, or this connected graph works. Also, if I use this formula, it'll be the same thing here. V is 6. F is, what was F? F was 5 minus E, which was 9, equals 2. And then, so if I was to work this out, 6 plus 5 is 11, minus 9 equals 2, which equals 2. So that makes sense. If the numbers are the same, then that means the formula makes sense, okay? All right, I'll stop.